Today I would like to present you a current project I've been working on. I'm a student of the Submicrotech University in Besançon, France, and in our studies we did a project on an unstable chemical reactor. The idea was to design a decoupled state feedback controller for a nonlinear continuous process. To start with, I want to introduce you to the reactor simulation we simulated. It's an exothermic reaction, and we have some system variables. First of all, we have two states. We have the concentration, Ct, and the temperature, T, inside the reactor. These two are continuously changing as we input different materials inside the reactor. We have two inputs that can be manipulated. On the one hand, the concentration, the type of material we input into our reactor. And the second is the temperature we use in our coolant circuit around the reactor. So this is not inside the reactor, it's exterior, and it helps us to cool down our reaction if needed. Our reactions can be described in the equations seen in the top right corner. We see a product A being reacted with water to give a product B that we then want to sell. The entire simulation was converted to a Simulink model and is from now on called the non-linearized model. To start with, we will analyze this model to understand its behavior. When looking at the model and doing simulations, three equilibrium points can be found. The first and the third point are stable, while the middle point is unstable. It is precisely this middle point, which is unstable, that is especially interesting for our reactor. So the goal of this project was to design a controller that stabilizes the reactor around this equilibrium. The fact that the second point is unstable can be shown by a linearized model around the local point. By doing so, system matrices A and B can be found, and the eigenvalues of A are calculated. The result is a negative eigenvalue, but also a positive one, stating and providing proof that the system is really unstable in this point. In order to stabilize the model, not only the goal was to push the eigenvalues in the left half plane to stabilize it, but the idea was also to decouple the structure. The idea behind is to be able to use the controls C and TC to steer the concentration inside the reactor and the temperature inside the reactor as desired. This is shown in the diagram at the right, where the two crosslinks at the right side are undesired. Ideally, we would like to have a free decoupling. This is not feasible with the classic place command known in Matlab. Instead, calculation is needed, more advanced calculation. In order to be able to control the eigenvectors, we want to go from the left diagram to the right diagram, where there is no intersection between the control of the concentration and the temperature inside of the reactor. The method chosen was to solve the fundamental equation I minus lambda I in order to decouple the links. This is possible because we have 2 degrees of control for our reactor, and therefore we have an additional control to use to have the decoupling done. You can imagine if a reaction heats and you put even more wood into a fire, for example, but at the same time you cool it down, you have more wood in the fire, while the temperature of the entire fire could still be stable. This is exactly the idea we want to use. After implementing such behavior, we would ideally see these two results. The system was simulated with a corrector term, and if everything works perfectly fine, we would see that changing the temperature does not affect at all the concentration, and vice versa. So here in this example, at T is 200 seconds, we change the temperature and we can see perfectly fine the concentration doesn't change at that time point. The same is true for 400 seconds. There we change the concentration, but the temperature is not changing. And after doing the simulation in Matlab Simulink, we see that the behavior we wanted is perfectly fine. We have found a controller for the linearized model, and with this classic controller, we have great decoupling, but just of the linearized model. Another problem we have is if we falsely calculate the matrix H, the pre-command matrix, we would have a static error mistake. In this case, this is not a problem because the Simulink model has perfect calculations, so this does not occur. But in real simulations, this would be certainly a problem. To solve this, the pre-command matrix H can be replaced by integrators. The idea behind is if we feed back the error that we see and integrate over it, the integrated term will solve the error to be 0, and therefore we can leave away the H matrix by just changing the structure of our controller a bit. You can see the difference in the plots at the right-hand side. The H matrix got replaced by the two integrators. The current error state gets fed back and calculated. And when doing the simulations, we see that the results are pretty much the same as before. Just this case, we even eliminated the problem with the static error that could occur in reality. Now there's another problem. In the real world, it's very, very easy to measure temperature, but it's very difficult to measure concentration inside a continuous reactor. As a result, it's better to create an observer that observes the inputs U and the measurable states, in this case T, and tries to estimate the concentration inside the reactor. Implemented in Simulink, it looks as following. In the green box in the middle, we have our linearized model, and at the right side we have an observer that is used to estimate C and T, and only has as input T, which is the only measurable value we have, and U, as this is the input. When simulating, it's interesting to compare the real temperature we wanted and the estimated temperature. It's logic that these two are very similar, as the observer has just to feed them through. But for the concentration, it's even more interesting, and in this case we see that the real measurement and the estimation, in orange here, overlay perfectly. So as far as we are close to the operating point, in this case it's the second equilibrium, we see that our observer has near perfect results. In the next step, I integrated the observer and the integrators to the nonlinear reactor. We will start from the left. On the left of this Simulink model, the input signals are created. I use 2 steps for C and 2 steps for TC in order to create functions of steps or port functions as we need them. Then we see the integrators. As explained before, these serve to eliminate the static errors. They are fed through KE, which is our corrector term, and the signals go upwards and to the right. We'll follow the upwards tray, where we see a calculation, and this calculation is needed to change from the relative values we used in our linearized model to the absolute values we need for the nonlinear reactor. This difference is because the linearized model works around the equilibrium, so only delta values are applied. But the real reactor and the real equations, they perform the real concentration. So in this case, we need to do the inversion. After the nonlinear reactor, we feed out the real concentration into a scope so we can observe it later. But also we do it for the temperature, and we only feed the temperature back into the observer, as this is the only state we can really measure in reality. Again, we do the transformation, this time from the absolute value to the delta value, and use the observer we found before. And the observer does its job and estimates the concentration inside the reactor and the temperature inside the reactor, which are both fed back to the integrators. This is our control loop. After doing so, we once again input values, set points, to our reactor and look at the differences. In this plot on the left-hand side, we see the concentration, in yellow the command, blue the nonlinear, so the real thing that's happening in the reactor, and orange the estimation. On the right-hand side, we see the temperature. In both cases, we are very, very close to the equilibrium point 2, and we can see that the concentration is following perfectly fine as long as the temperature is constant. So between second 4 and second 8, 9, I would say. But we see a small change as soon as the temperature rises, which starts at second 12. And we see that the observer misjudges slightly our concentration, but the system still remains perfectly stable. So in this case, just the decoupling doesn't perfectly work. And to find out why this is the case, I prepared a second simulation. In this simulation, as we see on the right-hand side, we change the temperature quite radically. We go relatively far away from the equilibrium point to prove the point. We see that changing the temperature rapidly and far away makes our observer think the concentration inside the reactor is different. This is visible as the blue line and the orange line on the left-hand side get further apart. Then the second part of the simulation is a ramp function that is added to the temperature at around second 5. We see the temperature rise, and with a very small delay, we can see also that the estimator does perfectly his job, while we can see at the same time that the concentration is constantly misjudged. We see that the estimated value stays relatively close to the set point, which is to be expected because the estimator returns that value, and therefore the loop will work its way out, so this is achieved. But at the same time, we see that the non-linearized value, the real value inside the reactor, goes far apart from the reality. So, as a quick point about our controller, near the equilibrium point, we see that our commands are perfectly stable. They have slight errors due to the observer, but nothing very important. But the further far we go away from the equilibrium point, the worse our estimation gets. This is as expected, as our observer is just a linear observer. Now I went a step further. I implemented also an LQR. This is a linear quadratic regulator, and the idea is to have an optimal energetic command. The equation of LQR correctors are a minimization of cost function, and we have the term Q that penalizes deviations from the set point, and a matrix R that reduces or that penalizes the amount of energy used. So we can say if the focus is more on the set point or on the energy consumption. The higher the QR ratio is, the higher performance and the more aggressive our controller is. The lower the QR ratio is, the more gentle the whole reactor is and the more energy efficient it is. I found the following Q and R matrices as shown below. I compared the same model with pole placement and with LQR in these graphs, once with and once without observer. This is very interesting, as we saw that the observer sometimes is faulty, but this allows us to better compare the two. We'll start with the temperature inputs. We see that the temperature inputs follow very fast, but the pole placement results are way better. The LQR needs a little more time, and when changing the values, I noticed that the LQR also did overshoots. So if I put the values too high of the LQR to penalize the set point, it was just overshoot, and I was not able to get the result of the pole placement. By contrast, I was able to tune the energy consumption, and you can see that both return pretty good values. And for a giant reactor, even a delay of 5 seconds is quite fast, to be honest. Now let's look at the concentration. These inputs were given at the same time as the temperature. And we can see, once again, for the pole placement without the observer at the top left, remember at t is 15 seconds, we had a temperature change. This is not visible without the observer. As stated before, with the observer, we see a small displacement, as expected. The LQR, on the other hand, does not have the dynamic decoupling. And in both cases, with and without observer, we see that at the temperature changes, I misspoke before, it's at 12 seconds. Sorry for that. We see that the LQR has not the perfect decoupling, so the concentration changes in both cases. So if we go back to the temperature, once again, just to see the difference, here in this case, we see temperature follows as expected, but the concentration, which is just way easier to manipulate, is not decoupled in both cases. So in conclusion, what did I do in this project? What did I learn? Well, I modeled the complex linear process. I linearized it around the unstable point. I synthesized a new controller, enhanced the design by using the integrators. Then I went on to design the observer, which is needed to observe unmeasurable states, and I compared the final result with an LQR. My key learnings were eigenstructures and also the decoupling of eigenstructures, as it's a powerful tool, and just using place as many tutorial states is not the best idea if needed. I validated my knowledge that, well, linearized observers only work in linearization, and I compared pole placement with LQR. I would like to thank you for your attention and have a great day.